Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody.
Welcome
to another episode
of
Ask Us Anything
About
Electrochemistry.
It's like we're finishing each other's
sentences
today. See, that was okay. That was still cheesy.
I just remember there was a movie about that, and like when they tried to finish each other's sentences, it just came out all wrong.
There's a bunch of examples of that, and one of them is yeah, it's a silly one. I think it was like it was a Disney movie. It was like Frozen or something, and they're like, we finish each other's sandwiches.
Yeah, that's right.
And it's like, oh, that's funny. Anyway. So yeah, I only wanted to do the silly words of our title. I thought that would be a nice touch.
Yes,
very important. So welcome everybody, and thank you for joining us. I guess should I get to the anonymous?
Sure.
Emails, I think
we got a question. You can always
after the webinar, I think it was.
Yeah, this was a question. So Neil, first and foremost, Neil just did a webinar this past Wednesday. If you haven't watched it and you're interested in learning about mod shocking and semiconductors, I'd highly recommend looking at it. It's on our YouTube channel, but it won't be, I would say, freely available forever. It will be archived starting December 1st. So if you haven't watched it already, I'd recommend taking a look at it. So it's on the Pine Research YouTube channel. If you're not already aware.
And thank you to those who did join me. I appreciate it. I had some good questions, and I enjoyed it. So thank you for those who watched live. Appreciate it.
Yes. There was a question. So people can ask us questions like clearly here live, and we'll try to answer them as soon as we possibly can. But sometimes you can ask us questions via email and just have us answer them live because you can't make it to the live stream. So there was a question from a person who wanted to remain anonymous, which is fine. And also, if you do send us questions by email, you also have the opportunity to provide us with some data or at least a picture of what you're observing so we can talk about it. We'll be able to talk about it in so much more detail. You'll get way more value out of this when we're actually able to see what the problem that you're running into. But this guy, we'll just refer to him as anonymous, was saying, I work on batteries and conduct EIS studies on cells that I fabricate. In some of my Nyquist plots, I've noticed that the semicircle is not well defined. Specifically, there isn't a clear second x-intercept. Could you please advise how to fit such data and extract meaningful information from these kinds of plots? Should I be checking for the Kramers-Kronig relations? He continues to ask, and there are many parts to this question. We'll tackle them one by one. But where do I have to use DRT, distribution of relaxation times? Because when I initially take a look at the Nyquist plot, I couldn't find if there is a possibility of multiple semicircles, multiple RCs hidden in it. And then lastly, he mentions if it is CV, like the shoulder of a peak or something like that, we could use a technique like square wave voltammetry to kind of accurately find the peaks. And similarly, how to even know if there are multiple RCs buried in a Nyquist plot. So there is a lot that this anonymous person is mentioning and talking about. But I think we'll start a little bit at the beginning, which is the situation where you have a Nyquist plot, you have you know some semicircles are not well defined, and specifically there isn't a clear second x-intercept. And I think you already have some.
Yeah, I have some data I can use. I think the second part of the question was like, how do I fit the data and extract meaningful information? Okay, so let me share our software here. I have some data that I can use as an example. So this is our software Aftermath Blue. So here's the first example, just to follow the logic here. This is like, actually, I don't even know what this data is from originally, to be honest. It's not that important. I get maybe an RDE or experiment of some kind. Anyway, I'm not going to worry too much about the specifics here. All I want to kind of note is that here's an example where I have, I mean, it's actually not, it's more like a Warburg short. Let's just pretend that this is two semicircles. I'm working with what I have here. I'm not a researcher, right? So yeah. I have the data that I have. It's as good as it's going to get. So this is like two semicircles that, the first one doesn't, there isn't like a super clear distinction between the two, but they both have there's a rightmost intercept. That's the point I'm making here. And, the anonymous's comment was like, well, what happens when I don't have one? So I'm just going to show you basically comparisons here. So the first thing that I can do is just kind of do a quick fit here. This isn't going to be the best fit, to be perfectly honest, and that's sort of on purpose. This isn't the ideal circuit, but pretend it is. Just let's play make believe together. Okay. Okay. So here's just a decent fit. I'm not going to tinker with it too much. The point is, okay, I have a rightmost intercept. And so your logic tells you, well, good, my fit is going to give me data. I should fix this value. It's driving me nuts because but I'll let it go. I have two values for capacitors, even though this one needs to go a little higher. And I have values for the resistors. And so you might tell yourself, oh, well, perfect. I have this completes down, like this goes down to almost to the x-axis. So that means that I can get data. Well, if I don't have it go all the way down, what on earth can I do? Which one did I want to play with? I think actually I'll just go to some real battery data. So this is actually a battery data. As you can see, it's a lithium-ion battery at 0% state of charge. And this is a case where it's probably similar to what Anonymous is kind of referring to. So there's first of all, there's a bit of ambiguity here. This looks like you could say one semicircle here and then another semicircle here. Or you might it almost kind of looks like there's one here and then there's kind of an inflection. This could be one or this could be two. I'll get to that point a little later about DRT and checking those kinds of things. But for now, what I'm going to do, and I know there's an inductive part, I'm just going to ignore that also. So let's just fit the same semicircle here, and I'll just kind of try to illustrate the point that I'm making here. And I'll do a few things just kind of quickly in the interest of time. And in this example, I'm going to exclude. It's a nice kind of feature in our software. I don't need the inductive nonsense. I'm just going to get rid of it. I don't want to bother with it. I'm going to I have to do a few things here because this is a battery, and batteries are a pain to fit for a couple of reasons. One of them is that they have ridiculously large capacitances and ridiculously small resistances. It's like the extremes of both units for the fitting algorithm. And the fitting algorithm is like, hey, what gives, man? So it kind of makes things a little bit harder until I adjust some of the min and maxes here. So bear with me. I'm getting there. All right, let's just kind of try to lock some things in. What am I at here? All right. Yep, this one isn't playing nicely with others, so I have to fix it up. Okay. And this, and that's too big. I'll get, yeah, it just doesn't always want to play nicely. So give me just a moment. I promise I will get myself into a decent fit. All right, there we go. All right, perfect. So here we go. The point that I want to make here, again, forget about whether this is multiple semicircles or not here. The point that I'm making here is that, okay, well, look, you might say to yourself, well, this semicircle doesn't complete, right? This thing is like only, I don't know, halfway or something. It doesn't complete. Well, would you look at that? I still have, it's massive. It's like 15 farads. It's huge. I mean, this is like a full 18650 lithium-ion battery. But so whatever. The specifics of this system I'm working with are not the point here. And I have a resistance of like 100 milliohms, give or take. Well, how did I get that? Well, the reason is, of course, because this is a mathematical fitting algorithm, and so I can fit this data and it fits what's there. Like the answer of like, well, my semicircle doesn't totally complete. How can I get data? It's like, well, because it can fit the first part of it and it extrapolates. So like this software isn't, I mean, I'm not going to, again, take more time because I know there's other questions. I don't want to belabor it too long, but like if I create a circuit simulation, what I could do is just extend this line of the fit and you would see that it would go down and eventually touch the x-axis. And presumably what that means is that if I went to a low enough frequency and I wasn't plagued by drift and other problems, my data would actually complete. But you don't have to have it complete. Now, the tricky part comes with when you ask yourself this question: how much of the semicircle do I need to get good data? That's the key. And that one isn't easy to answer, other than for me to say that generally, the more of the semicircle that is completed, probably the more accurate your data will be. But that being said, you do not have to have a full, complete semicircle like this, for instance, that connects down to the x-axis in order to get fitted results. You just don't. That's what the fitting algorithm is for. It can fit it. Now, again, just to reiterate, if you have, for instance, I'll just draw this one without the software for a moment. If you have, for instance, a Nyquist plot and you have, one semicircle and then like that, and you try to fit it, and you get your fitted results, it's like, okay, well, you could imagine that the fitting algorithm could assume that this is your semicircle, or it might assume that's your semicircle, because if you zoom in here, right, and you look at this data, it's like your data is just like that much of it. So it's like when the fitting algorithm is doing its thing, it's like it might assume that works, it might assume this works. In other words, this is like 10% of your semicircle, and so it's like, well, I don't know, you're going to have a huge variance. The more of the semicircle that's actually there, so the more your data, in other words, as low frequency as you're able to go, something like that, right? Like, maybe halfway is one way to think about it, as a rule of thumb or something. But by the time you have enough of the semicircle developed, basically, bless you, bless you.
Thank you. Sorry about that.
Then the fit is likely to be pretty accurate. And it's like, because the fit extends like far enough, there's going to be some like variation. Maybe like the fit will have, there'll be some like plus or minus, to some degree, I guess, but it'll be more locked in because enough of the semicircle is there. So that's kind of the way I'd think that through. Don't be discouraged if you don't have a full semicircle. If there's some curvature to this, this green line kind of curves like this, it'll give you enough to play with, and you should be able to get results. So that's kind of my answer to that.
So there's another thing I would that might be worth mentioning.
Yep.
Is if you simulate the data. So our software can also simulate it. You can actually
I didn't get into that just for time, but
you can pick a low frequency just to see like, oh, I didn't get to those super low frequencies. You can then see, oh, with your model, oh, I can actually get the line to go further. You were talking about it, and then like, oh, we can go this way, it can go that way, depending on what your fit is.
Yeah.
So that's another useful thing. But also, if you know that if you truly have one semicircle, just one, and you've guaranteed it, then if it's really a perfect semicircle, then once you know the radius, once you actually have like the halfway point, if it's a semicircle, then you know where it should end.
Exactly.
In principle. So that's another.
And in theory, if it's even a quarter or a third, I mean, you can kind of say, well, I could extrapolate. Like, there's ambiguity here because real electrochemistry data, real impedance data doesn't always behave perfectly well.
Yeah.
So there isn't an answer like, this is how much of the semicircle you need to have to get good data. It's a sliding scale. But generally speaking, you do not have to have a full formed semicircle in every instance. And that's almost never the case in reality. It just doesn't happen that often.
Yeah.
Even in the example I showed first, where the rightmost semicircle hits the x-intercept basically. Well, the space between the first and second one didn't like dip down to the x-axis because the time constants were close for the two processes. Like you don't always get like this perfect like semicircles that act so nicely and behave themselves. Like that's not how reality works. And we're still able to do analysis on that. So hopefully I kind of make that point clear. There's two other points as part of this question that I'll cover, and then we will move to the live questions. Thank you everybody for your patience. The other one was, it was Kramers-Kronig. So my answer is yes, do Kramers-Kronig. Okay. That's my answer.
That's your answer.
Always. Like whether you have a semicircle, no semicircle, it hits the x-axis, doesn't hit the x-axis. It's Thursday or it's Monday. I don't care. Do Kramers-Kronig. If you have a good software that has an algorithm that does it well, do Kramers-Kronig. It's always a good idea to get at least some check on the validity of your impedance data. Yes. Okay. And then the last point is on DRT. So first of all, if you have a suspicion that one semicircle is multiple processes, just do DRT. So it's like, well, when should I do DRT or where should I? Well, if you have a suspicion that you have multiple charge transfer processes, just do it. I mean, it's just a mathematical analysis. It's not a data, it's a data manipulation. It's not, there's almost no downside to doing it other than that you might misinterpret the data. But I mean, like, if you're like, well, should I do it or should I not do it? It's like, well, if you have it in your software, just click the button and do it. Like, you're not going to hurt anything. You might as well see what you get. That being said, as it comes to the analysis of DRT, when you should not do it or when you should sort of be cautious about
like the range of frequencies.
The range of frequencies or the interpretation of the data. DRT is not applicable when you have highly capacitive systems that have a specifically large ZI or y-axis compared to the ZR. So for instance, if you have a data set that looks like a battery data set, for instance, that looks something like on the Nyquist plot, it's easier to see on the Nyquist plot. If you have something like this, then that's supposed to be a D. D, R, it almost looked like a P. So DRT, happy face. Yes, you can do DRT because this is, I shouldn't undo. I'm going to crash the program. This is minus ZI and this is Z real. Okay. Basically, you don't have much ZI. You don't have a lot of super. I mean, there might be capacitive behavior. They're definitely capacitive, but there isn't a pure capacitor, so to speak. However, if your data looks something like that, let's just say DRT frowny face, or at the very least, only do it here. That is moderately happy face. On this side, it's definitely frowny face. It's angry frowny face. Okay, so just you can't do it. It's without getting more specific. Again, trying to move on to the questions we have live. It's I see what you're doing over there.
Yes,
it's very important. The point is, it is DRT. I'm probably not going to say this properly. I'd have to like read some papers again and make sure the verbiage I'm using is not maybe right. The capacitive, the purely more purely capacitive or mass transfer, what would you call it? Behavior in frequencies of this, like this part of a Nyquist plot, basically, is in violation of the assumptions of DRT. So it won't. Like, you might actually get like some crazy amount of like what looks like modulus peaks or something that indicates all these, and it's like a false positive or a false flag or whatever you want to say.
It's like that's all diffusion.
Yes.
But you would get like lots and lots of peaks if you actually tried to fit it, sort of say, with DRT.
Exactly.
It might not. It won't. And even so, even if it showed up as one semicircle, it's like, well, I have 3 charge transfer, it's like, no, you have 2 charge transfer and 1 diffusional tail.
Yes. So cut your data off. Don't change your data. Just clip the end, basically. And the rule of thumb for DRT is to like use the data only if it is close to the x-axis. as a general rule of thumb. Now, of course, what does that mean close? It's like, well, that could be kiloohms or it could be milliohms. Depends on what you're doing. But the point is, if you have a capacitive tail, Warburg tail, whatever, CPE, that part of it is not, you can't, I mean, you shouldn't, you can't really do DRT. It's not, the theory of DRT doesn't apply there in those ranges. So just, that's the rule of thumb. So that's all I have to say about whether you should do DRT. It's like, in many cases, it's quite useful because especially in batteries, you have a lot of processes. You have an SEI, you might have other, capacitive things at the anode and the cathode. You have charge transfer processes. You have a lot of stuff going on in a battery. It's in some cases, at certain states of charge and certain conditions, states of health and whatever, some of those processes mesh together. The data set that I showed was like 0% state of charge in that case, for whatever reason, well, for actual reasons, but the time constants of the anode and the cathode are pretty disparate. That's why I got two semicircles, right? At like 40% state of charge, you kind of just get one semicircle, and it's almost for sure the anode and the cathode are in that set. Like, one of them didn't go away. It's just that their time constants are too close. So DRT would elucidate and like verify, oh, I still have an anode and a cathode, so I'd probably get 2 modulus peaks, something like that. So, but I would just have to limit my DRT analysis to the places that are not overly capacitive, something like that. So I hope that kind of covers. Anonymous, if I don't know what your real name is, but if you recognize these questions, and
yes,
hopefully
you
watch this. Yeah, exactly.
Watch this.
Hopefully that kind of covers your questions a little there.
Yeah, and if you see this and you actually want to show us what your data looks like for next time,
yes,
we can do that too. That's fine. So the next question we have is from LinkedIn, from Roya. Roya asks, and I think this is a very interesting question: which battery is better? The one that reach to the maximum voltage sooner, and the one that reaches later, if all the conditions are the same. So, I think this is kind of interesting because we always think like, oh, a battery, has a maximum voltage, and I'm assuming it's like, okay, you're charging it to the same rate. Which one charges faster or something like that? It's an interesting question. It's also a very vague question. It also suggests like, well, all the conditions also can't necessarily be the same if the maximum voltage is reached sooner or later, because first off, just from what I've learned from you, it's mostly been like, well, the battery has a capacity. It's just like, this is how many milliamp hours or amp hours of charge the battery has. So you can't have 2 batteries with different capacities that get charged at the same rate and one be getting there faster or slower.
It's a bit of a contradiction in terms, to a certain extent. The question is a contradiction in and of itself. Right? It's kind of like, as I've said, we get the question about like, I did the same thing twice, I got different results, and my answer is like, I'm sorry to hear that, but you didn't do the same thing twice.
Or your system changed.
Right?
Yeah.
You don't think you did, but science and electrochemistry specifically is just awful. So, the direct answer to your question, in theory, which is never going to be reality, so just heavy preference, heavy
grain of salt.
Yes.
Let's just call it that.
Heavy caveat, whatever.
Heavy caveat.
I can't think of the words today. English is hard. Everything is the same: the mass, the capacity, the materials in the battery, the style of the battery, the shape of the battery, the mass of the battery, the capacity, the specific capacitance, the power density. Everything is exactly the same, which has never happened in reality, even in the same 2 commercial cells built on the same factory line. However, if it were, the one that got there later is better.
Interesting. The one that got there later.
Because it lasted longer. Means it lasted longer. I mean,
yes.
Like, you're charging everything with the same exact amount of amps, same C rate for the same mass or whatever, and one of them got to your higher voltage sooner. That's the worst one.
Because it most
the one that lagged longer means that it charged for longer, which means it could deliver more current for a longer period of time. So it's better. It has a higher specific capacity. That would, by time times current, gives you milliamp hours. It would have a higher number of milliamp hours than the other one.
Interesting.
So that's the answer.
I did not think that. I was thinking like, oh, if it charges faster, then it's better. It got
No,
to
if
the
it has,
voltage.
if you're putting an amp through two different batteries at the same time,
Yes.
right, and one of them is done faster, it no longer can deliver energy. The other one still can because it's not done.
Interesting.
It's delivering energy longer.
Okay.
So-
Okay.
So,
Yeah.
So the one that lasts longer is better.
Mhm.
But again, there's probably other reasons why that happened. Like you had a slightly different mass.
Mm.
So if you have twice the mass, it should last twice as long. But it only lasts 1.5 times as long. So you think it's better, but it's actually worse because proportionately it didn't last as long. Like there's a million ways we can go with this, right? Which is why it's the theoretical thing is kind of interesting. But I hope that kind of makes you think about this, right? It's, as a general rule of thumb, the battery's purpose is to store energy and then deliver energy in the form of electrochemical energy, right? So it's converting chemical energy to electricity power to make your phone last so you can scroll TikTok for the next 13 hours. So if you can't scroll TikTok anymore, you're very sad because it got to the lower voltage too fast. And then you sit there crying because you can't see cat videos or whatever people do, kids these days. But if your battery is not at the voltage yet, you can keep watching your videos and be very happy. So there you
go. Hopefully that answers your question. Angeliki had a question, but she retracted it.
Okay.
So I was going to, I asked if you wanted, her question was about, EIS and interpretation of semicircles, although you were exactly talking about it.
Yeah, probably what I talked about before inadvertently maybe answered the question. So if you are still here, Angeliki, that might have addressed what you were talking about. But if you have a follow-up or you want more clarification, just let us know. But it was retracted on YouTube, I guess.
Yeah, it was retracted on YouTube.
Perfect. Then we'll move on.
We'll move on.
So
Anand Maru is asking, in double layer capacitor, why do we actually write Cdl and Rct in parallel? Why not in series? That's a very interesting question. That's a good question. I think
it is a good question.
Yes. I think my 2 cents on the subject is, even though technically speaking, I think if you were to actually think about a real electrochemical cell and system, there's a good argument to be made why it would be in series.
It's the very first nanosecond.
For the fact that for the potential to actually be the potential, it's a capacitor, sort of say.
Yeah.
It has to charge first, and then the current goes to the resistor.
Yeah.
But often it's the case that the current that flows in an electrochemical cell for like a cyclic voltammetry experiment, the Cdl and Rct is describing charge transfer at a electrode-electrolyte interface with a redox species. Usually you'll get current that's associated with both the charging of the double layer and a Faradaic process. These two currents are, you do it in a cyclic voltammogram, you get both of these currents at the same point in time, but they are associated with two different things. And because you have them at the same point in time, it's not like one thing has to happen and then the next thing. It's that these two processes occur in parallel. Some of the current goes the direction of charging the double layer, and some of the current goes the pathway of Faradaic reactions. So to that
point, I just had a kind of a brilliant idea, because this was related to what we were talking about, you and I, yesterday.
Oh yes,
with the potential. So exactly what you said. An argument can be made that in the first like 1 nanosecond, actually, any charge transfer resistance will have to happen in sequence with the capacitor setting up, because at right away before anything happens, there is no double layer. Like literally no potential can flow into the solution. Like nothing can happen until the double layer sets up. So like at the very initial case, you could argue that this is kind of the situation. Okay. However, after a nanosecond, which is to say that anytime you can measure anything, at your surface of your electrode, right? What you actually have, and this is a couple ways of thinking about why it's parallel. One of them is that in a parallel system, let's say we have a capacitor at the surface. So this is our inner Helmholtz plane, right? These are positively charged, whatever, ions, and we have a negatively charged electrode. Okay, so this is our capacitor, right? I'll try to draw a capacitor here. So this is our capacitor. Okay, that's just ever present, and we have electron transfer that can occur at the same time. Now a couple of things. For a parallel circuit, the current that flows, so I'll just draw electrons, right? They kind of are going to go, depending on the impedance or the resistance, in some mixed way. So it's like, maybe like 50%. It's not exactly true, right? It depends on a lot of systems. But like half of the current might have to go towards the double layer, while half of the current goes towards the charge transfer process, depends on the potential and all these things. However, the voltage is the same across both. So that's one of the keys here, I think, is that the voltage just across, if this is your circuit, like whether it's electrochemistry or it's just physics, if this is your circuit, the voltage is the same across both of these, right? In a parallel circuit, that's physically true. And actually that tracks because we know, for instance, that the voltage, that the electrochemical potential, if you will, and Alex, you have that slide that kind of shows the potential, but like the potential at the electrode also extends into the double layer. So basically what we're saying is that the potential that we're at, that's, let's just say the potential that's encouraging the charge transfer reaction here, the RCT, the potential of that is also the potential that's in the double layer, because it has to be. And so we have the same potential occurring. If we had a series, that would not be the case, right? If this was the case, there would be a voltage drop across here, like something, and then there would be another voltage drop across here. The voltage that I'm applying, or the potential, right, that my potentiostat is applying or whatever, would be like split. And that just can't be the case. Like we have to have a potential to drive this RCT reaction, and that potential has to be the same at our double layer. It looks like a smiley face again. So part of it is you can rationalize that way. But then the other, I think, would just be sort of very generally speaking, is that because after the initial time where there isn't any capacitor, once the double layer capacitance sets up, it's always there. So it's always present. It's always at the surface. So then when a charge transfer reaction happens, it has to sort of, this is where you have heterogeneous versus homogeneous electron transfer. It depends on whether you have tunneling or it can reach the surface, all that kind of other discussion. But the point is, when an electron is transferred for an oxidation or a reduction reaction, it's sort of happening through or with the double layer being there already. It's already there. It's at the surface, right? There's no sequence. It's already, they're both happening in parallel simultaneously at the same time. And they're both impacted by the potential that is being applied, because that potential extends into the inner Helmholtz plane. So maybe that kind of explains it a little bit for you. I don't know.
Yeah. So Anand, I hope that makes sense. Great question though. I think it's I always like the questions that are a little fundamental. Like,
I know,
why do we choose this circuit versus this circuit?
It's a good question.
It's a good question. Next we have Calvin. Calvin Chung has a question. What if your Warburg tail is not straight? I sometimes get some curving down at the end. It sort of looks like two semicircles, but the second semicircle isn't complete, for example.
Sounds like a Warburg short.
Could be a Warburg short. Yeah, absolutely.
I think, in fact, that's kind of the one that I had here.
Yeah, you want to?
Yeah, I was just getting to it. So earlier I kind of had this example. Where is it? Oh, I think I had it minimized. What did I do? There it is. Okay. Earlier I had this example of what I call two semicircles. In reality, it's actually a Warburg short. So what you can have maybe I'll just simulate it actually, rather than fitting. It might be a little easier to manipulate, kind of showing what you are talking about. So I'll draw the circuit that might be relevant for what you're talking about.
Now they can't see you make it, but that's okay.
That's correct.
Yeah.
Because I did not share my whole screen.
Yes.
So what I'm drawing right now, you are not seeing, because I'm very, very good at this kind of displaying live streaming thing. So I'm just going to keep talking.
But you'll be able to see it.
You're going to see it very soon.
It will happen.
I'm drawing a circuit for you, and there it is. Now you still can't see it. Now you can see it because it popped in a different window.
Now you can see it.
It popped up in a different window.
It's very small, but you can see.
Yes. So this is the circuit that I drew. It's basically it's a Randall circuit, right? We have a resistor and a CPE or a capacitor, and then a Warburg short is in parallel with the capacitor in series with the resistor. So it's a pretty standard circuit. Okay, so what I'm going to do is manipulate it and kind of show you what you might be seeing. We don't need a huge ohmic resistance. Let's make this a little bigger. So here's a case where I need an infinite plane. So let's do this. Okay, so this is like a Warburg. This is an infinite Warburg. All right, so this is what you're saying, oh, well, it's okay. That would be an ideal situation. Now, what you're saying is it's like curving down a little, but it doesn't make a full semicircle. So you might have something like this. Yeah, maybe like that. So here, and this is like a kind of an ideal situation, but I have, oh, it looks like it's a Warburg, but then it's kind of curling down. So the options in front of you are, it's just an infinite Warburg, and this part here is drift and noise and error. So do Kramers-Kronig. If you observe that it deviates at the end here, then that might be an indication that like it is just an infinite Warburg, and all of this curl at the end is just, it's drift. Like this is low frequency. So sometimes at low frequency, the points kind of scatter around. They might be inaccurate. So do Kramers-Kronig and see how well it fits the end of your data. If it is actually real phenomena, it's fitting Kramers-Kronig and it suggests it's real information, you might have a Warburg short. A Warburg short is a somewhat of a hybrid, if you will, circuit element, if you're not familiar with it, where it is describing diffusion like the Warburg like the Warburg infinite does. Okay. But it's through a fixed boundary length. And so depending on the length of your boundary layer and the parameters of your Warburg short, you can get what looks like a complete semicircle. Okay, so you can see that what I'm doing is I'm adjusting one of these parameters and it's causing it to curl down more or not. And I can kind of go to extremes where it almost looks like, it's just a semicircle. It's not even diffusion. I can talk more about the Warburg short if you want me to. All I'm kind of showing you here is that just this is one possibility for an option, that it could be a finite Warburg element. So it's still diffusion, but it's through a fixed boundary length. The regular Warburg that looks like this is an infinite, semi-infinite plane diffusion. So it's just diffusion into the bulk forever. This is when you have diffusion through a fixed length and the boundary condition is absorbing, basically. So that is very possibly one of the ways that you can interpret that kind of impedance data if, as I said, the Kramers-Kronig doesn't show you, for example, that it's actually just kind of noise and drift, which does happen at low frequency pretty frequently. So do Kramers-Kronig, as I said.
Yeah, and if it is a Warburg short after the first semicircle, you should have a 45-degree angle, at least for a little bit.
For a little bit, yeah.
Before it actually starts to curve. Right. But if you don't have a 45-degree angle, it's like, oh, well, maybe it's actually just another semicircle.
Yeah, exactly.
So that's another thing to look out for. Again, of course, ask us, continue to ask us questions for clarification as we continue to move on. Jesse has a question. I asked for a little more clarification. Maybe he can talk more about it. I'm trying to get a power curve, get the power, did a voltage sweep, and then multiply the current measured with the OCP, and my power curve looks off. I plotted power against OCP. So I think we need to know a little bit more about it, because I was like,
this is a contradiction in terms.
Yeah.
You're not plotting power against OCP. The power at OCP is 0.
Right, because you have zero current.
Right. I hope you mean potential.
Yeah.
Because if you're saying it looks off, it yeah. OCP definitionally is the potential where there's zero current.
Mhm.
Power is current times voltage or potential. So you're constantly multiplying zero current times some potential. Your power is zero at OCP by definition.
Mhm.
Okay. Now, if you're talking about I did a voltage sweep and I multiplied current versus potential, not OCP, and I plotted power versus potential, that is a power curve. Now, if it
Mhm.
looks off, that's and that's what you mean. Perhaps you just used a different term and you meant potential.
Mhm.
Otherwise, if you're talking about OCP, then you might have made a mistake in what you multiplied, right? But if you did multiply current times potential or voltage, and you produced power, and you plot the power versus uh, power versus potential. I have
No,
some.
Jesse says yes, you are correct.
Okay, let me. I do have some data for this too. Actually, I have data for everything. Can you believe it? But where in the world is it? Probably in. It's probably here. So I'll show you what it should look like, and maybe you already know this, but I have a polarization curve for a solar cell
Mhm.
that I'll pull up. And I know the problem, Jesse, might be that you say, well, it looks bizarre. And it's like, well, I'd have to look at it. And it's like, okay, well, what am I supposed to do if I can't look at it? You know, obviously you're into this fundamental thing here. So let me see if this power curve, this might not be the most ideal power curve. I have no idea if this is going to work. I'm going to try it anyway. And hopefully it doesn't look ridiculous and fall flat on my face here. Let me make this a little bit thicker so we can see it. So here's a polarization curve, for instance. Actually, I think now that I'm thinking this through, I think you might be plotting the wrong thing. I think you want to plot power versus current, and that might be the problem. So on a polarization curve, voltage is usually on or potential on the y-axis, and current's on the x-axis. So when I make my power curve, I know you also can't see the mathematical operation. I'm just going to multiply x, y, make a new trace. So here's a power curve. Just move. So this is typically what you get with a power curve. This one's not. Make it. It's two red ones. I want a blue or something. That's okay. So I think the problem is you're plotting power versus potential. You should be plotting power versus current. So this is typically what you see is that you'll see a maximum somewhere close to the mid to the end of the polarization curve. So this for a fuel cell, for instance, you'll be dropping the voltage from whatever the open circuit is, usually 1.2 if it's a PEM or something like that, down to zero. The current, shoots out to the right and then drops off at some point. This is a solar cell; it's behaving a little differently. But this is what your power curve should look like. But again, I think you should be plotting power versus current, not voltage. I think that might be your problem. So give that a try. And if it still looks weird, you might have. I mean, you could try emailing us, and I could take a look at it. Again, it's one of these things where like it's hard for us to comment without looking at it. So anyway, that's what I can say about that.
Yes. Okay. All right. So just moving on. There is Verses of Gold had just a little comment that about when we're talking about RCT and CDL. Parallax has a question. I'm trying to, I guess, do a little bit of research on the question. But Parallax is asking, I'm relatively new to studying electrochemistry. For me, it's quite challenging. Yep. To understand Kohlrausch's law. Could you please explain it? I'm 16, so treat me like an extreme beginner. I am trying to read about Kohlrausch's law. It's not exactly. It's basically Kohlrausch's law is known as of independent migration of ions refers to electrolytes limiting
that's right.
molar conductivity to its constituent ions, which is to say that the limiting molar
it infinite
conductivity is determined of, like, say, sodium chloride is equal to the limiting molar conductivity of a sodium ion and a chloride ion. That's equal to the
I learned this
sum.
one a million years ago. I'm not sure I remember how to explain it well enough. It's like the infinite, isn't it? Like the conductivity is the sum of the at infinite dilution, something like that.
Yeah, it's just like the conductivity at infinite dilution, like, but infinite dilution.
It's just because I think it's one of these where at infinite dilution,
Mm-hmm.
things behave more ideally. So you don't,
Well,
have to, you
yeah.
don't have to deal with activities, something
Yes.
like that, right? It's kind of like
Or
how
it's purely
the ideal
activity.
gas law only works at low pressures and high temperatures.
Correct. Yeah, something like that. There's definitely certain conditions.
Yeah.
But then it has to do with, like, a mole or something, or I mean, I guess maybe stated simply, if the molar conductivity of the constituent ions, so you have your anion, your cation, and if one of them has a low molar conductivity, well, or it's the molar conductivity of both, it's just a sum,
Mhm.
according to the example I'm looking at. Basically, it's just saying the molar conductivity, the limiting molar conductivity, is the sum of the two of the ions that make it up. So if the molar, and I mean,
I don't know that I can explain it very well, so I'm not sure I want to take a big stab at it, to be honest.
yeah,
It's not it's a this is admirable of you, Parallax, truthfully. You're 16.
yeah.
And so you're really broaching subjects that are pretty advanced. Maybe I learned about this in high school. I don't remember if I learned this high school chemistry or in college. And to be honest, it's not something that I'd have to like read up on it to exactly remember. It's not something I would say used quite as commonly in like the research, I don't know, level of electrochemistry, which is where we're sort of operating more. So I guess you'd say, it's kind of a fundamental chemistry, academic kind of a topic. I'm not trying to minimize it. It's it's certainly a valid like chemistry topic. It's just not something I feel like I am able to explain without sort of a refresher. I probably have to look at like my old college or high school notebooks if I have them at home somewhere. I'm sure at some point I learned Kohlrausch's law and probably did some homework problems or calculations on it and something, and it's not something that I'm equipped to really explain, unfortunately.
I'm looking at a couple
Mhm.
just like things, I guess. Okay, so because I'm trying to wrap my head around like infinite dilution, like when you have something that's infinitely diluted, it has less conductivity. But actually, there's I just found this just on a website. I think this is perhaps helpful, but if you're, hopefully you can see
Yeah.
this.
Very good.
So basically it's just saying, oh, it's the sum. It's just like in all these cases for sodium chloride, whatever your salt is that dissociates, right? You put table salt in water, it dissociates. Its dissociation, molar conductivity, if you will, is equal to the sum of its constituents. But this is the picture that I think is very interesting, which is to say that as you move to lower and lower concentrations of your analyte, or sorry, your electrolyte, whether it's an anion or a cation, if a strong electrolyte is a nice linear relationship where, like, oh, if you decrease the concentration, the molar conductivity, assuming infinite dilution, starts to go up. But in a weak electrolyte, it actually doesn't follow a linear relationship. It actually curves, and the molar conductivity starts to increase dramatically at at very specific concentrations. And I think this just has to do with, as you said, the nature of ideal analytes or ideal electrolytes, salts and chloride ions and stuff like that. When the concentration is low and they act as an individual ion, this tends to go up. But here, if the electrolyte is very strong, it's linear. It doesn't actually follow this kind of weird behavior. I don't know. I'd have to think more
Verses
about
of
it.
Gold added the comment that the ions do not influence each other at infinite dilution. Electrostatics are weaker. So the idea is the little bit of conductivity essentially
Yeah.
that they add at infinite or at low concentrations,
At
if
low
you will,
concentrations. Okay.
act independently and just add
And then just
and
add
just add up. Like,
conductivity.
you have like
Okay.
one.
So no
What's conductivity?
intermolecular
Like
forces.
Siemens, you have like 1 millisiemens of this and 3 millisiemens of that. It gives you 4 total. Like it's something like that, right? It's just a very easy. But if you have like a huge amount of stuff, there's all
Right.
these
If-
electrostatic interactions
Yeah.
between them,
Yeah.
and it's not like 10 plus 10 equals 20. You get different effects.
Correct.
So it's something like that.
So
and
it's something like that.
That's the without doing any real math other than
Yeah.
stupid little arithmetic here.
Okay.
It's something like that, right? In
Mhm.
terms of the theory, but yeah, teaching
Okay.
it theory wise, I'd have to review.
All
To be
right.
honest, I'm not equipped to really talk more elegantly
Yeah.
about it.
Okay. I think that makes sense though. If you have ions in solution and you assume no, because that was like infinite dilution. It's just
Right.
like, well, it just means they're not interacting with each other. Then the molar conductivities, which is just how easy it is for the ions to act as conductors.
Yeah.
Just like how a metal or a specific thing acts to conduct
I
electrons.
feel like someone talked about that recently.
Oh yeah. Then it becomes easier. It's the sum of those constituents or parts. So parallax, I don't know if that's very helpful. We actually kind of rarely get this type of question, but thank you. Hopefully that's helpful. Okay, all right, let's move on. So, and this is one that may also be a little tricky for us to answer as well. From Shujit is asking, can you explain DRT from EIS data? I know we can know the different phenomenons from it, but I need a more clear explanation on it. How exactly DRT becomes more sensitive?
More sensitive? That's a good question.
Well-
Well, the one thing that I mentioned earlier in the live stream when I was talking about questions at the very beginning, so back up like 45 minutes or 50 minutes or something, is that DRT cannot be performed if the data are very capacitive or diffusional, mass transfer-y. God, those are words.
Those are words.
I'm having trouble speaking today.
It's okay. It's Friday.
It is Friday. My brain is already shut off, so my apologies. So if basically on your Nyquist plot, if the y-axis data is really high, if it shoots up, if you have a Warburg tail, you have a diffusional tail, you have all that kind of stuff going on, DRT is not appropriate. So that's one way to talk about, I guess, the sensitivity part of your question. You could say it's not sensitive, or more accurately, it's not appropriate to do DRT on data like that. Again, I feel like I had it in my brain before. I'd have to, I've in some literature and investigation of the theory of DRT and how it works. There's a reason why that is it's a violation of the theory of DRT. It's like the DRT is no, I know why. It's because DRT is a mathematical transformation, okay, of impedance data, assuming that you can break it's kind of like Kramers-Kronig in a way, which I don't want to open a can of worms. So apologies if that's too much to think about. But what it's similar in the fact that it's a deconvolution and a transformation of the data, assuming that the impedance data can be represented by basically an infinite series of time constants. Okay, so that's what it means. Distribution of relaxation times. The times part of that is it's recasting your impedance data as a sort of an infinite sum of RCs. Okay, so resistor capacitors in parallel and adding those up. Now, an infinite number of RCs with different time constants, which is the multiplication of the resistor times the capacitor, would give you a million little semicircles, like a million bumps, right? That's what the Nyquist plot would look like. What that doesn't look like is a straight line going straight up. It can't. That would be a pure capacitor or a pure CPE or a pure Warburg element by itself. So what it means is that when I'm trying to assume to find all of the places where I have a distinct time constant, which is what I'm doing with DRT, I'm saying it from 0 to infinity, like seconds, of time constants. Where does my data show me that time constant exists in my data? It has to be something semicircular, basically, or which was why I said before, close to the x-axis. Like the data can't go up forever on the y-axis on your Nyquist plot. It's a violation of the transformation itself. So in terms of sensitivity, it will be less sensitive if you have a big y-axis, big capacitance, big mass transfer part. That's one way to sort of think about that. And so then explain DRT from EISD. I hope that kind of explains it. It's a manipulation of the data, assuming you can mathematically describe your EIS data as an infinite sum of RCs. That's what it is. And then it's finding where you have distinct RC time constants in your data by frequency. That's what it's doing. I hope that addresses it. If that's too technical language or something, you know what I mean? I know that might be like, I don't really understand what you mean. Please explain. Shujit, let me know if that isn't clear. But I hope that's what I think is the most direct answer to your question.
I'm also gonna put a thing into LinkedIn. There was a recent publication by the ACS electrochemistry on DRT. There's this like tool called drttools.com. Mm-hmm. And the paper itself actually goes into a little bit of DRT, but it at the end of the day, it is a mathematical transformation. Yes. And frankly, it's like, I don't know enough about the math, but it's like, you have an integral from negative infinity to infinity, and it's based on some time constants and stuff. And so when a computer, but at the end of the day, it's like, well, mathematically, it's this integral, but a computer, isn't, might not be able to actually calculate like a definite integral. It might create like an analytical solution. So the nature of the DRT results that you get will be kind of a function of the parameters that you implement, which is what their part of their argument is. So you adjust it, but if you get these peaks, it'll help with at least being like, oh, for this one semicircle, it's actually two semicircles. There's two time constants associated with it. But being able to, well, we can't really go into the math in details, which is really all it is. It's just a math.
Which is why I brought up Kramers-Kronig, because technically Kramers-Kronig is the same thing. It's just mathematical transformation to different set of equations, which again, different things, but it's a similar phenomenon. Kramers-Kronig is checking for the validity of the data. DRT is checking for the presence of disparate time constants, or RCs.
Yes.
But that's a good point. Yeah, that's a good new publication to check out if you're interested in DRT.
All right. So
where are we at here?
We're at Ali.
Yes.
Ali is, I think, is asking, if we do not have access to a potentiostat for a 3-electrode electrochemical system, is there a way to perform the experiment with 2 electrodes? My research is on the 2-electron reduction reaction. So
I think we answered this.
Oh, we answered this last time?
We answered this last time, and it looked like, I think you left a comment on our video. I tried to answer. We could talk about it again, but I tried to answer comment on YouTube, Ali, as best I could. But you could talk about it again briefly if you want to.
Yeah, no, I mean, you can do things in a 2 electrode setup with like a battery. Like you're just doing your organic chemistry reaction, basically, is what it sounds like. 2 electron oxygen reduction type of thing. And you can, it's just the knowledge that you have of what potential, how much current, some of those things are just unknown. I would also mention, I don't know at what scale you're doing things are, but um, it's funny because in the time that Neil and I have been doing these live streams and stuff, we occasionally get these questions like, oh, I don't have a 3 electrode potentiostat, or I don't have a potentiostat, and I'm doing this very simple experiment. And I just want to at least make the point. Pine offers very inexpensive potentiostats. You can get one, labs burn through like thousands of dollars a day just in doing research in chemicals and stuff like that.
Yeah.
We sell some potential, the lowest cost potentiostats around like $3K. And it gives you so many different capabilities. Some you might not even need, but it will be enough to at least get you started and allow you to do the research. Because it's one thing to just like say, okay, how can I do a thing with just 2 electrodes and have it be questionable, inaccurate, not able to be pushed forward for like a publication. But it's like, okay, if you just spent a little bit of money on this thing, you can get good quality data and push your research further. So I just want to let you know that like that's a thing. You can, of course, hook up a battery or some power, an inexpensive power supply, do a 2 electrode experiment, and like, okay, you can tell people that you used a 5-volt battery, plug 2 electrodes into your system, performed your 2 electron your 2 electron oxygen reduction reaction, maybe generating some peroxide or something. But then the reviewers can ask a bunch of questions like, well, how much current, how much whatever, what is the actual potential of the electrode? And that's just going to force you to do the experiment again with a potentiostat.
Yeah.
So,
and I know obviously we recognize in some cases geography can play a role in your access to equipment. So yeah, those
are things like that.
Understand the difficulty you might be under. In some cases, in situations like yours, you might have a local company maybe that is able to make equipment or supply from elsewhere. So sorry if that's kind of the constraints you're under.
Okay.
It's only you're in a tough situation. You obviously can't do very much about some of those those situations. So yeah, all I can kind of do is extend our sympathies, I guess. I'm sorry. There's nothing we can do about that. Obviously,
we try.
Yeah, exactly.
we try our best, but I guess.
Yeah. So the long and short, Ali, is that you just won't know what voltage you're at. You won't know what potentiostat you won't know what potential you're at. If you have a 2 electrode system, you're doing 2 electron oxygen reduction, you're producing peroxide, whatever you're doing. You can do it. You're unfortunately not going to know what potential you're at. So you're going to have to hope you're at a, negative enough potential or something like that.
Yeah.
And it might drift around and it's tough. You're not going to likely have as easy a time, frankly, without a reference electrode. So I wish you luck. I do. You're in an unfortunate situation without the ability to use a reference electrode. Honestly, because something like oxygen reduction, it actually is quite important to know what potential you're at, because you're looking for onset potential, you're looking for over potential, and you can't know those things without knowing where you are. And if you don't have a reference electrode, you don't know where you are.
Yeah.
So,
sorry, man.
Yeah.
Appreciate it.
Best of luck to you.
Sincerest condolences. I'm sorry. We try to help as much as we can.
Yeah.
Okay. All right, Ali. Okay. So moving forward, because we do have a bunch of questions that are coming in. Thank you all for asking them. Sheik is asking, Chica's asking, if the angle is 80 degrees instead of 45, can we still consider it a Warburg? That's a great question.
Probably not.
Yeah, so it would at best, you're getting something like a Warburg open, right? Like maybe if it's going like this and then it's going up,
Yeah, something.
it could be a Warburg open. Like you have a semicircle and then it's going up. Then that's the other kind of direction it can go to. But it should be a little bit 45 degrees before going like directly up. So, but yes, if absent of any other information, if it's 80 degrees instead of 45, it's probably not a Warburg.
Yeah, that sounds more like, I don't know, what you'd call like non-ideal capacitance, basically. But I sort of use this analogy frequently when I'm talking about this and when I do my impedance webinars. I like to think about it this way, where one of the reasons for instance, the alpha or the n coefficient in a constant phase element, for instance, because a constant phase element, for instance, with alpha equals 1 is a perfect capacitor, and a constant phase element with alpha is 0.5 is a Warburg. It's a 45-degree angle. So anywhere between 0.5 and 1 is something in between a Warburg and a capacitor, right? Now, one of the ways that we explain the presence of 80-degree angles or 85-degree angles or 0.9, 0.8 alpha values that aren't perfect or ideal is heterogeneous surfaces. So for instance, a capacitor is a perfectly flat plate, but the surface of my electrode's actually like it's not flat, right? There's bumps and bruises, and someone punched it and it's not polished and it's not flat microscopically. And so that's, it's a capacitance, but it's actually like there's porosity, there's all this stuff. So that's one way we kind of use to explain non-ideal capacitance, for instance. But another one that I like to describe, and it's to your point, is because a follow-up question, for instance, could be, okay, well, if 80 degrees instead of 45 is too far, I wouldn't consider that a Warburg. Well, then is 70 degrees close enough? Is 60 degrees close enough? Is 50? At what point am I close enough I can call it a Warburg? It's a good question. Thank you for asking it. Let me answer. It's admittedly ambiguous. The best I can kind of liken it to is a video that you made recently on understanding Warburg impedance, and the way you can think about a 45-degree angle.
I think I made the video a year ago.
Was it a year ago? It feels like it was recent.
I know.
It feels like it was recent.
We'll actually check for a minute, like about Warburg impedance.
Yeah. Well,
I made that in March.
Okay.
So
Okay,
it
good.
wasn't that.
I don't feel so bad. It was like
there was another video I made last year.
It's like 8 months ago.
Yeah.
Okay. So it's halfway between long and not long.
Yeah.
So we're both
exactly.
right. Okay. I was like, oh gosh, pretty soon it will have been a year ago. Then I'll feel old. But when you have a 45-degree line, basically what it means is you're moving the same distance on the Nyquist plot on the real and the imaginary axis. And the way you can think about that is that the real axis is distance, the y-axis is time. Okay, and so 45 degrees is a way of thinking about the particles are moving in the at a set distance and time. It's the particles are moving like away from the surface at the same, like based on the diffusion coefficient. You think about centimeters squared per second. It's like a plane moving at a certain speed away. Okay, well, what if it's moving a little slower? Right? If I have electrode surface here and I have ions here, that's a capacitor. If I have the ions moving away, that's diffusion. But what if the ions are kind of moving, but not that fast? Is it a capacitor or is it diffusion? Well, it's kind of both, right? So that's one way that I kind of think about 80 degrees, 70 degrees, 60 degrees. It's some mix between diffusion and capacitance. It's like with a steeper angle, again, thinking about the x-axis is distance, the y-axis is time. It's not moving a lot of distance over the same amount of time. So it's like taking longer. So it's like particles are diffusing, but they're not diffusing that fast. So it's like I said, it's I have a capacitor where one of the plates of the capacitor, you could think almost, is kind of moving diffusionally in some way. Now I know it's kind of silly. It's like, is the inner Helmholtz plane like drifting away from the surface? Like, it doesn't kind of make sense if you think about it like that. But there's something about the idea of thinking about diffusion and capacitance happening sort of together. Something like that. That's a way that I conceptualize it.
Yeah. So when I think so, if you read like Mark Orzum's book about impedance, which I always recommend people at least take a look at, it's dense.
It's very dense.
It's very dense. But the example that he gives for Warburg opens and Warburg shorts, and your case is something more like a Warburg open, is when you have a porous electrode. And so in all these Warburg cases, you're talking about a redox reaction, diffusion controlled. But the diffusion, the electroactive species is in a porous material. So let me actually, I think it might be easier if I just draw it. So imagine if I start drawing this. So you have your conductive electrode, and then I'll use blue here to represent some kind of porous structure. Right, and inside this porous structure, I've got my analyte. My analyte's all up in this porous structure.
All up in there. Get all the way off my back.
All the way off my back about this. But beyond this, here, there's like no analyte. So no analyte. No light. Right, I don't have any of it beyond this. So the molecules that are right here, that's the arrow in the wrong direction. These molecules have no problem getting to the surface. That's kind of like your semicircle, your first semicircle. But the molecules further out, right? The molecules that are kind of further out, they take longer. So that's a little bit of your Warburg tail. There's a time that it takes for the molecules to get here. But when you're actually beyond here, well, you don't have any more molecules, right? But you still have a frequency. This is when things tend to go up. This is when you have like technically it's 90 degrees, but 80 degrees is when your molecules, you no longer have them. And the frequency, remember, these points represent low frequency, which is to say lots of time. Like, this represents the time it takes for this molecule to get here is kind of represented by these middle like frequency parts of the EIS spectrum. But on the low frequency, that's like all the way out here. It's like, this is the time scale for a molecule here to go to the electrode surface.
It takes forever.
It takes it. You've given it more time, but it doesn't exist, and because it doesn't exist, it doesn't actually. You don't get any real impedance. You just have this imaginary impedance.
It's all made up.
So that's a way that I think about it. That's a way you can kind of conceptualize it. And so when you think about why you're getting 80 instead of 45, you can think about, all right, do I have a porous electrode? What is my analyte? Where does the analyte exist in my system? Because maybe that's kind of, maybe it's not, maybe it's actually a little bit stuck in the pores, but maybe it comes out a little bit. Maybe that's why you don't get exactly 90. It's actually, at the time scale, low frequency, we have lots of time. Yeah, you're actually still able to pull some molecules that are outside of the pores, but still takes a while for them to get there. So that may help you rationalize the EIS that you're getting.
It's helpful because it's a rehash of that video you made yesterday.
Exactly. yeah, exactly yesterday.
March was yesterday. I'm old, so like a year is like a day.
Yes.
Proportionately, because I've been on the earth for 900 years. So, it's just a proportionate thing.
Mm-hmm. All about proportion.
For some reason, that video is always to me like you made it yesterday. I don't know why.
Yeah, and I was thinking,
I reference it a lot, and I'm like, because I love the concept of time and distance. Like it's a really cool way of
It's a
thinking
way of
about the
thinking
Warburg.
about it. Yeah.
And so it's like every time it comes up, I'm like, oh yeah, you just made this video.
Yeah.
It's like we've had like 15 videos since then, and somehow I still think it's yesterday.
Yeah,
This is just
know.
a me thing. I have no idea what's wrong with me.
Yeah, and I was kind of confused because oddly enough, some of the dates that I post videos just so happen to be like interesting, like weird days. Like I actually posted the chronoamperometry video on like September 11th, which is like an important day for the United States.
Yeah.
But I posted the Warburg impedance one on my birthday, like March 18th. So, and I'm like, purely coincidental. It had
it was.
No, it was just like, I
Sure
managed to finish the video and it checks all the boxes by these dates.
Totally coincidental.
Totally
huh?
coincidental.
I see how it is. You just gave yourself a special birthday present.
Yeah, that's right. My birthday present's getting this video.
Your birthday present is checks notes.
Checks
Warburg impedance.
Yeah.
Boy, do you have an interesting life. I hope that my loved ones get me an inductive loop for my birthday.
Yeah, that's right. I want to have an inductive loop.
That's what
on
I
my
really
birthday.
want.
Thank you.
Boy, we're this is what being old. For those of you who are in graduate school or younger, just know this is your future. It gets so exciting.
And for the holidays, I want my stocking stuffed in shorts with shorts. I don't know. YouTube shorts. I don't know.
My favorite joke about stocking stuffers is that a severed foot is the ultimate stocking stuffer. It's a little gruesome.
It's a little gruesome, but
it's funny because it just makes you think about it. And I just think it's really funny because it's just a tongue in cheek.
Oh yeah, that's right.
Like, I guess it is.
I guess it is.
The ultimate stocking
the ultimate stocking stuffer. Okay, moving on. VJ, because actually we still do have a decent number of questions.
We'll
VJ is asking, how can we measure the conductance value, infinite dilution of ions, at sub-zero temperatures? I don't know if this is related to what we talked about earlier, because it almost sounds like the I'm not gonna pronounce the name right. Kohlrausch's law. Kohlrausch's. Thank you. Kohlrausch's law. Because I also think about Kirchhoff's law. Kirchhoff's law, which is current and stuff, but
voltage circuits,
but this one, I mean, so I guess Neil and I we always think about the measurement of conductance through impedance because conductance and impedance are generally inversely related to each other. And EIS, impedance, gives you the added benefit of actually having a frequency dependent conductance, sort of say. At what frequency do these things happen? So there's a part of me that says to make the measurement that you want to do with whatever the system is that you're studying, because we don't know what the system is, perform EIS, take the inverse of the impedance, and do it at sub-zero temperatures. There may be some very interesting experimental considerations you have to think about. If it's a traditional electrochemical system.
Well, it could also be like an LPR thing. If you
could be an LPR
impedance, that's what I mean. Like whether you do impedance and you're able to do impedance, maybe you don't have a potentiostat that can do it, or what the case may be. But getting the impedance or resistance value right in ohms, but like you said, to basically, the quickest thing to do is to take the inverse of it, as you said. That gets you Siemens, which is a conductivity or conductance, sort of a measurement. But the other way to get a resistance or ohm value is to do a very slow voltammogram, essentially, around the open circuit potential, and you get the slope of your IV curve, and that's also resistance. So I just want to throw that out there. If you don't have impedance, but from an electrochemical perspective,
that's right.
From an electrochemical perspective, it's like whether it's at cold temperatures or not shouldn't matter, as long as you're able to get data. Like if it's so cold, everything's frozen and there's no fluid movement, you might not be able to get data at all because like it's a block of ice, whatever. But if you have cold temperatures, well, you can still do electrochemistry, provided there's electrolyte and ions and everything, right? So
that is true. Okay, all right. Next question is from Pega. I think that's how we pronounce it. Pega's asking, is it possible to perform EIS on an industrial scale electrodialyser?
Electrodialyser.
Dialyzer.
I thought it said electrolyzer. What's it?
I'm assuming this is for like electrodialysis, but that's
Electrodialysis.
also a topic I don't know very much about.
Yes. Oh, so you use an electric field to move stuff through an ion.
In principle, this kind of reminds me of in principle, you can do EIS on anything.
Well,
You
yeah.
you literally hook it up and then do the thing.
You can do You can do EIS on like a birch tree if you want to.
Yeah, that's right.
Impedance is a magical technique that's both simultaneously a pain to
Yeah.
get good data on, and also the easiest one to get data on in general,
Yeah.
because of the nature of having high frequency and having a non-invasive kind of a thing. You can get impedance on systems where DC electrochemistry just gives you nonsense. So there's that. I don't know. I actually have not used or seen an electrodialyser. Dialyzer.
I guess
Is
dialyzer.
it dialyzer or dialyzer?
Dialyzer.
Dialyzer. Probably dialyzer.
Dialyzer.
Yeah. I was thinking more of electrolyzer, but electrodialyzer.
Yeah. Okay. And so some of these things look like they're used for like desalinization and stuff
Yeah,
like that.
you can migrate ions, and so you
Yeah.
can get rid of
Yes.
salt from water, things like
Yes.
that.
Oh.
Yeah, absolutely. You can
Yeah.
do. It should be absolutely possible to do
I
it.
think I'm actually working like there's actually a person who I'm working with who is trying this very thing. He's just calling it a cell, but I think
Mhm.
based on it doesn't the device that the guy's using this on is not for cleaning like salt from water dialysis.
Yeah.
But it is pumping water into seawater in his case into these cells. And yeah, I think you definitely can. I mean, this doesn't look all that different from like a fuel cell in the sense of like you have stacks of membranes and anodes and cathodes in series.
Yeah.
And you're going to get some interesting EIS results. And I would imagine a system like this almost not all that different from like a battery. Like it's designed to be kind of like pushed very low impedance, but if there is something odd, you'll see it in the EIS. You may have a lot of inductance though, because the cables that are connected to these things are huge. So that's one thing to be careful of. But I guess the answer is, I think the answer to the question ultimately is yes, because it is possible. And this reminded me of like how you can do EIS on anything. Because one time, one of my friends from high school, we were asking, I think someone was asking like, is it possible to eat something, or is a certain thing edible? And then my friend just said, in principle, anything is edible. You can technically put anything in your mouth.
So,
but it's not really a good idea.
So here's a better philosophical question.
Yes.
And this is definitely electrochemical related. And by that I mean not in any way, shape, or form. Is edible mean that you can physically put it into your mouth and like, right? Or does it mean that it can actually be eaten and digested? Because if it's the former, then I agree with you.
Yes.
But if it's the latter, then absolutely not everything is edible.
Yes, that's correct.
Right? Like I could say tree bark is edible because I can rip off a piece of birch tree. For some reason, trees are you can do impedance on trees. You can also eat them.
But you probably could digest tree bark. You can't digest a rock.
No, you can't digest it.
Oh, birch.
You can't digest. I mean, you could eat it and swallow it,
and
it will go through your digestive system. And probably come out the other side. This is not going in the direction I want to continue. But my point is, like, your body can't digest. It's a cellulose, right, or whatever. Like your body can't.
Okay.
Your body
Let me ask
won't
you this.
do anything with it.
Can you cook? Okay, let's say you had cooked tree bark. We cooked the tree bark, right?
Yeah.
So because we do eat things with cellulose, we can break down plants and stuff like that. Tree bark is just super hard.
No, but it's like celery. You can't break down celery. It goes right through your body.
But we would say celery's edible though.
I actually would maybe argue with that contention. yeah, that's actually interesting. I mean, celery, first of all, as a food, it's cellulose and water. Like that's all it consists of.
Sure.
I think, right?
Mm-hmm.
I'm pretty sure. And celery is one of those fun foods where, like, I remember, I assume it's still true. I learned this like forever ago, but it's like your body uses more energy, quote, digesting it than it gives you.
Yeah.
And I think the reason for that is that, again, what does edible mean?
Yeah.
You can eat it, chew it, and swallow it. and your body will not break down any part of it, which means that the energy that your like digestive system takes to move the mass through your body, as it does with any food, nothing is absorbed. There's nothing to absorb except water. So it's partially nutritional in some sense, but otherwise,
But-
the cellulose is just not.
But we also don't
processed or
we also don't define edibility by a net energy positive, like we gain calories from
that's
it, right?
true, and I'm not making the argument based on caloric usage.
Okay,
but I am making the argument based on the fact that your body, your stomach,
Yes.
acid processing mechanisms that when you eat a piece of steak, break it down and convert it to energy. And whatever,
And what
right?
other stuff.
Yeah, like it converts it to, ATP and biological processes, and it helps you continue living, right?
But it's just like Prime Minister right now. Like
Yeah,
said,
exactly.
Talking about
This is very important discussions. So I think this is another discussion that really needs to be dug into at another time, but it's a very important discussion. What is edibility?
what is edibility?
But here's another
Yes.
parallel argument.
Uh-huh.
For example, when you talk about something, everything's edible, you could talk about what's a children's book, right?
Okay.
And so here's a similar argument.
Yes.
Every book is a children's book if the kid can read.
Yeah.
That's what I'm
okay.
saying.
Yeah.
It's a
Technically,
book.
It's a book.
He's a child.
Yeah.
He can read.
As long as he can read
Therefore, it's a
it,
children's
it's
book.
Therefore, it's a children's book.
I mean, if I bought the Encyclopedia Britannica for a child,
what's an encyclopedia?
oh, I don't know. It's the internet printed on paper.
Oh,
it's
it's the
a
internet printed
thing.
on
It used to exist. I don't know if they still do. So yeah,
Yeah,
this is-
that's a good question.
How did we get talking about
Well, we
this?
got talking about
'Cause
this
impedance
because
doing
it's like,
this?
can you do impedance on an
on a tree.
electrodialyzer?
Oh, that's right.
And I was like, well, principally, you can do impedance on anything.
Just like you can anything.
Just like you could eat anything.
Just like anything is.
Just
a-
like
is a
anything
children's
is
book.
edible. Just like any book can be a children's book.
Wow, this conversation has gone a little off the rails, but I regret nothing.
Oh, I regret nothing too. Hopefully, Pega, you've learned a little bit
Hopefully, we've all
about
learned a little bit
EIS.
about impedance, electrodialysers,
Yes,
edibility, and readability.
and readability.
And we've learned a little bit about ourselves along the way.
yes.
It was about the friends we made along the way.
Yeah,
I don't
absolutely.
know.
So Anand has another question.
Is there an above? I don't know what I'm.
Yeah, so that's the thing. I don't think we have an attached.
I'm checking our email. I don't see, for example, like an email. I don't know if you've sent one.
Check one in Pinemeyer or nothing.
Yeah, no,
okay.
there's nothing.
I'm seeing inductance behavior in the graph attached above.
I don't know what.
And I'm also gonna see because there's
They
no
are all cylindrical cells.
because you can't attach a graph in
YouTube on the chat.
on
Yeah,
the chat.
I don't think that's.
Looking there too.
Yeah. So Anand, it's possible. So if you've sent it to our PineWire email, it's possible that it got caught by like our spam filter, and in that case, we would have to wait a bit to get it. So apologies if you sent it, and we'll get it later. If we get a graph like later today or so, something, when our filter sort of gives us the ability to grab it or what have you, we can talk about it like next week. Is the best I can kind of offer to you, but I don't have anything to look at, so we can't comment, unfortunately, at the moment.
Yes. Yeah.
So yeah, sorry about that, at least for now.
Yeah.
Until then, I guess we'll move on. So Shivam has a question. If there is a small curve bump in LSV, as if it goes up and goes down again, in an HER region, what could be the possible reasons? Well, what you're describing might just be the other part of a bump that goes down. Like you're saying it goes up and then down again.
Like a peak, like a CV peak?
Yeah, like
It's just
LSV. It says LSV. So small curve, it goes up and then down.
Yeah.
HER. Like so. So just from a clarification perspective.
Hold on.
Like if you're talking about an LSV for hydrogen evolution, I'm just thinking out loud here.
Yeah.
Drawing. It's right around 0. Let's just say, right. Let's say you have like you know, something like that, or it like maybe it makes a peak or whatever. There's something going on, negative, whatever. So are
Yeah.
you saying that you have like you're scanning negatively and you have this, and then it goes down or something, and this is like a peak you're talking about, or are you saying it goes, you know, down and then it goes up and then down like that, and you're calling this a peak? Because my interpretation is, for instance, well, that's just the crest after this peak. Like
Yeah.
this is the peak, and it's like, oh well, then it you know, it crests before going back down again. Like this is, in other words, when you have this shape, is this the peak or is this the peak? Like, you know what I mean? I'm confused. So
Yeah.
like that's the clarification I'm asking for. If it's the blue one, if it's this where it's like you're scanning negatively and it just sort of like
Goes down.
goes
Or
up
goes up.
before it does anything, that would
Yeah.
be bizarre, because it's like when you're scanning cathodically, like negatively,
Yes.
you would expect the current to go negative, like, you know.
You said yes, the first one.
So the blue
Wait,
one,
the blue one?
you're saying it's
okay.
like the blue one.
I think so.
That's so it's like you're scanning negatively and then it, or it's the
And
red
then-
one, the blue one. So
The
you're
blue
getting
one.
you're scanning negatively and the current goes up before it drops to do like the HER. How in the world would that happen?
Trying to think. Yeah, if it's scanning and
So it's like you're
kind of
scanning
flat,
negatively and it goes up. So
it's
the
doing
only
oxidation.
times, I shouldn't say the only times, one of the instances that I can explain a little bit where when scanning negatively you get a positive peak is something like organic oxidation. So for example, if you do something like like uh, like uh, like methanol oxidation or ethanol oxidation on like platinum or palladium or something like that, what the CV sometimes looks like is it's an oxidation, so you'd expect positive current. So it's like when you scan positively, you get a big peak like this, and then when you scan negatively, you also get an oxidation peak. It's a really weird system. You don't get a negative peak. It does not happen. You get a positive peak in both directions. There's I can talk probably a little bit about it. I'm not sure that I would have to remind myself some of the literature as to why this happens. It's a very kind of odd and somewhat
Yeah.
unique phenomenon, because not only is it not reversible, obviously, because you get this, but the fact that you get another peak that goes up on the reverse scan is just really, it's frankly, it's kind of weird. And it's hard to kind of wrap your head around. Like this kind of peak makes sense from all the reasons that we understand why peaks happen, but like going this direction, why does it make a peak and then go back down? It's strange. So that being said, all I can think as a possible explanation based on what I just described is maybe there's some organic oxidation occurring if you have a noble metal catalyst, because I know that is a thing that can happen. Otherwise, I mean, I don't know. Is there like under potential deposition over, like there's sometimes there's weird stuff like that happens that I don't frankly understand that well either. I've seen those terms used or whatever, like
I mean,
you get weird phenomenon that occur at like potentials are not supposed to happen sometimes.
Depositions are
I
still
don't
reduction
know.
reactions, though.
Yeah, so that
It's
doesn't.
still reducing a metal or something. I have a
Tin cobalt phosphorus coated on nickel foam. Okay, so it's not a noble metal. As far as I'm aware, this phenomenon occurs mostly with noble metal catalysts. I don't know that it wouldn't occur. I think it's possible as an explanation. You have some organic, but if you're just doing HER and you just have like standard electrolyte, tin, cobalt, phosphorus coated on nickel foam. I wonder if one of those things is oxidizing.
So even one thing I would also ask is,
Like
I know you're doing LSV, but can you also do CV?
Yeah, can you go back?
Can you go back? Can you look at, if you're able to, like, you do LSV specifically for HER to make TAFL plots to get some kinetic information. but I feel like there is some fundamental chemistry questions that we have about this system.
And can you also do something like this?
Okay, all right.
So
he's
to
thinking
your
the
point,
same thing.
to your point exactly.
Mhm.
If I'll use blue again because that's the color I used. If
Yeah.
the test that you did, you got something like this, that's like your test or whatever. To Alex's point, can you do CV? But can you do it between here and here? So like keep your range limited to this weird phenomenon, but don't go too far into the other region. So like do CV where you go like here and then back. What do you get? Do you get another peak, or does it flat?
He said CV curves are normal on the catalyst. CV curves are normal on the catalyst, which
So-
means I'm assuming the CV curve in the absence of the substrate do not provide like a quote catalytic current.
CV curves are normal
so
on
they're
the
normal on
catalyst.
catalyst. Okay, so CV curves are
I-
normal on catalyst.
I think it's possible one of the like metals or materials, which I suppose is nickel, cobalt, phosphorus, or tin,
Yeah.
are interfering or reacting in some way. It's bizarre that it would react that way, as in oxidative something on a reductive scan. But nickel has many oxidation states that it can do and things like that. Cobalt as well. I'm not so sure about tin, but tin has a lot of different oxidation states, I think. And I don't know if something like that is occurring. But yeah, CV curves are normal on the catalyst. I don't really understand how the CV curves are normal, but the LSV isn't, and what that.
Yeah.
No, it's
Oh,
car alarm.
Hopefully
Anyway,
it's
not
not my
me.
car alarm.
I don't think it's me. No, I do it.
Okay.
So yeah, maybe
The curve
it's
is in the negative region only.
Yeah.
CV curve is in the negative region.
so yeah, I
Yeah.
Um,
So the CV curve. So Neil's right. The CV curve and the LSV should, because they're technically both doing the same thing.
Yeah.
Just CV's just going back.
yeah, exactly.
Because I would also change things like the scan rate. I would do a scan rate study as well. I would change the potential range because maybe something's being formed. I'd also look at the current. I mean, it sounds like from what it sounds like the magnitude of the current is within the realm of all the stuff. So it's not like, oh, this peak is actually very small and it's like it's negligible. But
Yeah.
um,
Well, hopefully that kind of talks through some of it. I don't know if we've given you enough answers here, but there's
Yeah.
definitely some curiosity here. I mean, the organic oxidation thing I described, I have no idea if that explains it. It might not. That's just one example of that backwards sort of looking peak when that happens in experimentally. Or part of your catalyst, as I said, is oxidizing in a bizarre way. Check the standard potentials for tin, nickel, and cobalt. See what potentials they
if it's an
can
oxidation, those-
oxidize or
Yeah.
whatever at, and see if maybe that potentially adjust for your reference electrode and your pH and stuff like that, and check if you're possibly observing part of your material that's reacting, like the catalyst itself. Like it's not hydrogen or anything like that. It's your actual catalyst. That could be part of it.
Yeah, I have to
Change your electrolyte, see if it's the same.
Yeah, I think I'd also have to look at it too. That might be helpful.
Yeah, it could just be noise. It could just be
Yeah.
could be not even real, or I don't know, something like that.
Yeah,
right?
yeah.
So
Hopefully some of this is a little bit helpful, but
yeah,
yeah,
it's an interesting phenomenon for sure.
Yeah.
So yeah,
we don't have a definitive answer.
Yeah,
for you.
there's only so much we
Unfortunately.
can kind of do without seeing it and without knowing exactly what's going on.
Yes.
Yeah.
Okay. All right. Figuring out where we are. So Elijah has a great question. I'm glad that he asked it. Please, what's the lore behind the background meme? I do EAS especially for corrosion studies at OCP. Anything wrong?
What's the lore?
That's
the
the
lore
lore.
is me being triggered constantly by this
Yeah.
question.
Welcome to Neil's TED Talk.
Yes, welcome to my
I'll
TED
be-
Talk.
I'll be
Okay, so
honoring.
to be clear, you're doing corrosion studies, so I don't think your results are pointless. I think you're okay. You're the exception to my rule. The lore is this. This question happens on this live stream, and it happened once during my webinar on Wednesday. This question plagues me, and it bothers me. It bothers me like deep in my soul, and that's a me problem, and I'm working on that. But it bothers me, and I feel justified in why it bothers me. Is that I get a question, something like, "What potential should I do impedance at?" Something like that. That is a question in variations that I get pretty often on this live stream and otherwise. I want to do impedance. What potential should I do it at? Should I do impedance at OCP? Should I do it somewhere else or whatever? And I believe I understand why people ask this question, but I hate it. I hate the reason, not that I hate why I understand why people are asking it. The reason why people are asking it, if I'm correct, which I could be wrong, but my assumption is that people pull up impedance on their potentiostat software, whatever potentiostat, whatever company they're doing. And when you click, potentiostatic impedance or whatever it's called in your software, the default that comes up is like, okay, I want to have a conditioning period or no conditioning period. I want 10 millivolt amplitude, and I want to use a set point. What set point should I do? And the default is just usually 0 versus OCP. That's just the default. And the reason why that's the default, I can tell you as someone who works for a company that makes potentiostats and writes software and has to choose defaults in our software for when people add an experiment, because that's just how software works. We just pick something. Now, we could pick 712 millivolts versus AGCL, or 900 volts versus NHE. But we don't do that. We just pick 0 versus OCP because it's just a logical value to put into the software as the default, thing that fills in the box, right? When you fill it in. And for some reason, there is this tendency for the average researcher to look at that and say, that means I have to do it at OCP. Like, I guess I can't change that number. I guess that means I have to do impedance at open circuit potential. And for some reason, when they pull up a cyclic voltammetry or an LSV, and they see the box filled in to go from like 0 to 1 volt at 100 millivolts per second, they don't say to themselves, I guess those are the limits I have to do. They say, well, I'm studying the oxygen reduction reaction, so I need to go like 1.23, and then I have to go negative, and because that's where the oxygen reduction reaction happens. Or they say, I'm studying the ferrocene reaction, which happens at about 0 or 100 millivolts or whatever. And so let's go from like minus 500 millivolts to plus 500, and let's scan there. And well, if I want to study the oxidation reaction, I need to be at like 200 millivolts, because that's like positive of 0 by a little bit. I'll have an overpotential. Or I might want to do electroplating chronoamperometry, and it happens at minus 600 millivolts. So I should apply minus 700 millivolts so that I get my plating to occur. And that will give me a negative current, and I'll get my nice film. And I should apply that current to make sure I get my electroplating. And then they say, I want to see what the impedance is like of this electroplating reaction. And they just, all of that knowledge, all of that logic just goes right out the window. All of it. Everything I just described is how an electrochemist thinks until they click impedance. And it baffles me. I don't understand it. It's like your electrochemistry brain goes out the window. If you're trying to study a reaction that occurs at minus 600 millivolts, whether you're doing bulk electrolysis, chronoamperometry, square wave voltammetry, super ultra amazing awesome voltammetry, or electrochemical impedance spectroscopy, why would the logic change? You're trying to study minus 600 millivolts, so apply minus 600 millivolts or minus 700 millivolts or whatever. That's what your baseline should be. Well, what's your open circuit potential? Is it 0? Well, is the reaction happening at 0? No. Then why would you apply 0? Because your software had it at there initially. Like, it's just, that's why I made this meme, because it drives me insane. I don't know why your brain shuts off. It's like people think of impedance as some mystery technique, and I get it. It's hard. But like, if you're trying to, it's like, what potential should I do impedance at? What are you trying to study? Well, I'm trying to study this reduction reaction. What potential does it happen at? Minus 600 millivolts. So apply that potential, and then you're going to study it. Like this is the same logic that you would use in any other situation. So that's the lore, if you will, behind this meme. And thank you for coming to my TED Talk.
Well, remember what one thing, and maybe for the next time you do an EIS webinar, this may be a confusing thing, but you mentioned to have valid EIS, your system has to be stable.
That's correct.
Right? It has to be stable, it has to be linear, it has to be causal. Well, most people might think, well, hey, if my system's at 1 volt, where the thing's happening, it can't possibly be stable.
Sure,
right? Because it's like, well, the reaction's happening, it's not stable. So
yes.
So maybe that's, they're looking at a CV. It's like, oh, there's current that's showing up there. I can't, so I have to do an OCP, because that's the only potential where the system is stable.
Yes.
So maybe that's the thought process behind it. But yes, I'll allow you to
when
be on your soapbox.
That's right. I had to get on my soapbox. Someone asked me to get on the soapbox. Like, that's what Elijah did. Elijah just said, here's a box full of soap. You should
get on it.
So
thank
you for that opportunity, Elijah. It drives me nuts. It just does. I'm sorry. But so I made a meme about it, and I don't regret it.
All right.
So in conclusion, just do it at OCP. You'll be fine.
Yeah. Let's see. So the next question is from Misui underscore. What is formula of cell constant?
Cell constant?
Yeah, I'm not so sure I know what
I don't know what
you're referring
means.
to. I don't know. We don't know. I think we need a little bit more.
I don't know what you mean by cell constant.
Yeah, I don't know what you mean by cell constant.
If you mean time constant.
Yeah, there's like time constant.
Time constant is resistance times capacitance. So if you have an RC, a resistor and a capacitor in parallel, the resistance value times the capacitance value is tau.
Which is in units of seconds. Yeah.
Because ohms times farad dimensionally equals seconds.
Yes.
But if you mean something else, I have no idea.
Yes.
I don't know exactly what
We're very sorry. Misui underscore.
You have to say the underscore.
Yeah.
Shivam had one thought. I'm just seeing. I got some insights for what I should go next. I'll probably do
XRD and
XRD.
sample.
Yeah, that's a great idea, because XRD is going to show you the crystalline phases and maybe the grain boundaries and all these kinds of things. That's a great idea, Shivam. I hope you kind of figure some of that out.
Yeah, you made a non-electrochemistry technique to figure this thing out.
Yeah, exactly. Especially because you have like tin, nickel, cobalt. You have like a lot of heterogeneity, like different metals and materials present in your electrode. So doing some of this spectroscopy or microscopy or things like that might help you learn a little bit about the structure and what's going on. Lucas has a question. Says, hello, for solar cells, how to reduce the low frequency noise in EIS analysis. I work with perovskite solar cells and I have a lot of trouble with low frequency noise. I'm working in OCP with one sun illumination. I love this. I think it's silly. One sun.
Well, yeah,
There's
that's
one sun.
Yeah, that's
it's like Star Wars, where you have like, what if you're on one of those Star Wars planets where there's like 5 suns? Was that Star Wars or was it a different movie? I don't know. I don't like Star Wars that much. There's like 5 suns, you know what I mean? It's like if you're there, you have like 4 sun illumination. But if it's like it's sunset, it's like 3 1/4 suns, because one of the suns is halfway down.
Yes.
I'm a child. I don't know. Sorry. To your question here.
Well, also, I think it's important to also ask, how low a frequency are we also talking about? Because
you're probably talking about millihertz, I'm guessing.
If it's millihertz, like single millihertz, experiments that take forever to do.
Yeah, some of it's unavoidable.
Some of it is unavoidable with that kind of system.
So as the frequency goes down, the impedance goes up, generally speaking, right? So one of the things you can try, and this might not necessarily be successful, and it might be tough to accomplish because you are also doing, I assume, middle to high frequencies as part of your impedance experiment. However, if you consider the fact that the standard of light reaching, yeah. No, I know what you mean. I don't know why. I just find it the unit funny. One single sun. I'm like 10 years old inside. So no, okay. So if you think about the fact that the impedance gets higher as the frequency goes down, one of the reasons that we get noise at low frequency is that the resolution goes down. So for example, if you think V is IR, right? You pick the voltage amplitude as the resistance or the impedance goes up, the current goes down. So as the frequency goes down, let me draw this maybe on a PowerPoint slide so I'm not writing in the air again. I have a tendency to just write into the air. So if you think about resistance or impedance, Ohm's law, very broadly speaking, V is IR, right? So at low frequency, the resistance gets higher, right? So if the resistance gets higher for the same voltage, because you picked your amplitude, then that means the current goes down. So what it means is that your Lissajous plot, for instance, at high frequency, where the resistance is low, the current is high, you get a nice looking oval or line. But at low frequency, the resistance gets higher, your current, your response gets smaller and smaller. And so it's like your current response can just be at the limit of detection for your instrument. And so it can get fuzzy. That's one of the reasons that we can get poor data. So one of the things that you can do is increase your amplitude. Okay. So increase the voltage amplitude. So you might do like, 10 millivolts or something amplitude. So go to 20, go to 30 amplitude. Try a bigger amplitude. Now, again, what that's going to possibly do is cause problems in the high frequency. It can make it nonlinear because the resistance is lower. But what it might do is it might clarify some of the lower frequency points, possibly. Okay, so that's the first suggestion that I have, is to increase the amplitude a little bit. The other is to make sure that the light intensity and positioning. I'm sure you're probably doing this if you're working on a solar cell. You're probably pretty careful about this, but make sure it's very steady. Make sure it's like everything's really stationary and the light isn't shaking. Make sure that the illumination is really constant, because if it's fluctuating at all, like you wave goodbye to your friend in the lab and it's near the light, you'll get a fluctuation in voltage. You'll get a fluctuation in intensity ever so slightly. Like, don't breathe. Set the thing, go next door, go into the next building, travel across the country to a different location. Like, sunlight on solar cells is really finicky, right? A very small perturbation will affect the voltage. And so at low frequencies, that'll be much more pronounced. So just be very careful about that part of it too. And then the third thing I can say is that if all of those things you've done, you're very careful, and you're still not able to get good results, you just might not be able to, because sometimes at low frequency, you just have drift and there's not much you can do about it. That just can happen, unfortunately. So, I hopefully some of those suggestions help. So, okay, he says, okay, I've conducted a study to check what is the amplitude potential, which will not affect the pseudo-linear. Yes, exactly. So for 20 higher than that, it's out of the linear. Yeah. Okay. Yeah. So you might be in trouble with that one. And you could in theory think something like, well, if I just independently probe the lower frequency part, you could use like 50 millivolts if you don't start hot, you know what I mean? But then you're piecing together the impedance. So you could do like the first 3 decades at 20 millivolts to ensure it's linear, and then the last decade or two at 50 millivolts. but you might have a discontinuity in your data because it just, that's going to happen practically. It could. Now, maybe it works out. You could try, right? You could try from, I'll just make up these frequencies. This may not be the ones you're doing, but like, let's say you do like 100 kilohertz to 10 hertz with 20 millivolts. And then you do 10 hertz to 100 millihertz with 50 millivolt. And because it's at a lower frequency, you're still linear because the resistance is higher. That's one thought. Again, I don't know if that would work. Yeah, check on the fluctuation of the light source. Fluctuations and minor changes in the voltage will not likely appear at high frequencies because it's fast, but at middle to low frequencies, it can. Again, if all of those things you've done, very possibly you might not be able to do anything because low frequency drift is such a pain to work through as you're discovering. So hopefully that's a few suggestions. Maybe they work. Maybe you're still kind of struggling, but yeah, it's still messy, low frequency. Yeah, I sympathize with you. I've done a lot of impedance on batteries back in my day, and it's like batteries, you have to go sometimes to like 10 millihertz and stuff to like really see the like mass transport properties, and it's just a mess. Sometimes I would collect the data and use it, and just in a paper or in a presentation say something like, look, I know this data is noisy, but it's the best I can do. Like, you're sort of, which in my opinion, I mean, maybe other people have different opinions, is that you can have data that's not perfect and you can still use it and just be a scientist about it and explain it. Say, this data is admittedly drifting and noisy. Some of the results that I display here will be, admittedly have higher degree of error, so to speak, but it's the best I can do. There's unavoidable drift or something. So to a certain extent, you might just have to settle on that, I guess, is what I would say. I have a problem with interfaces. I'm trying to change the interfaces of the ETL and perovskite. Yeah.
I don't know what an ETL is, but okay.
Electron transfer layer, maybe. A good question. I'm not positive. Yeah, Lucas, good luck.
Yeah.
Hopefully that's a few things you can look at. Maybe you'll have some success or not. I don't know. Anand, I got your data. I'll talk about this very briefly. I think it's a pretty easy answer. You have cylindrical cells, and you said you have inductance. I think you said at high frequency. What did you say? I'll go back to your question.
This is the
data that Anand sent.
This is the Bodhi plot.
That's correct.
Okay.
It's the Bodhi plot. I'm sorry. I'm
going
back to his original. What is it? I'm seeing inductance in the graph on cylindrical cells. So what you're seeing is inductance up here in the high frequency. That's pretty normal. Cylindrical cells like batteries are going to have inductance. There's a couple of reasons why this can tend to happen. One of them is that inductance is a secondary mechanism of storage in a battery. An inductor is like a charge storage mechanism. It's sort of like backwards from a capacitor, but it's still fundamentally a way for charge to be stored. So that's one way that it is interpreted. The other is that with systems like batteries that have fundamentally very low impedance, inductive effects are more pronounced, which can occur in the cell cable and things like that. So, for instance, here, 10 to the 4 at the very right most part of your Bodhi plot, 10 kilohertz, for instance, is might even be too high. Like, you're not getting any reasonable information here. You might even need to start at a kilohertz or even 100 hertz before you have any data that's meaningful, so to speak. The inductance effect is pretty pronounced, partly because the overall impedance is so low, and the limit, the lower. How do I put this? This might be difficult to kind of explain here. The lower impedance limit that a potentiostat is capable of, which is what you're kind of seeing when you're doing a battery like this, the lower impedance limit of a battery, the lower impedance limit of a potentiostat is where inductive effects are most visible. the opposite of that is that the high impedance limit of what a potentiostat can measure is where capacitive effects dominate. So they're opposite. So that's just it. Batteries have low impedance. They push up against the limit of the instrument, and inductive effects are more visible, and they come from the cell cable and things like that. They're not really meaningful very often in terms of the battery itself, which is why we tend to just ignore them or fit them with an inductor, and we sort of are don't care too much about it. Which color is best? I would probably need to see the Nyquist plot and fitted data. I don't know that I can tell just from the phase angle Bode plot. I don't know that I don't know. All I'm seeing here is one of them, like the orange one, I guess, or the red one, dips first or more dramatically, which possibly indicates that it is reaching more of a capacitive or mass transfer kind of state sooner. It might mean that it has a slightly faster time constant, but I can't draw too many conclusions from it, to be honest. I would need to see more of the data. Just a phase angle plot, it's hard to exactly tell. Oh, they're supercapacitors. Okay. Yeah. So yeah, similar phenomenon that I described with batteries, but supercapacitors. It's similar. Maybe not exactly the same, but a similar kind of phenomenon.
Answering.
Yeah, I did see your question about PN junction. I'm sorry, I've run out of time, and I did cover some of that.
I sent him a link to the.
Yeah, is there one where you abstracted that from another webinar? Because I did show the PN junction.
In Machaki.
Not Shocky.
Right.
I mean, I did obviously in my webinar from Wednesday. I actually didn't talk much about the PN junction, even though I did.
Yeah.
But then there was impedance of a solar cell is another video, right, that you made. Like, is that a one that, because I did that in one of
a solar cell.
Maybe I feel like I have a slide on how a PN junction works. I feel like I've shown it in a webinar before. I might not.
I'm not so sure.
Maybe not.
I don't know.
I have a slide on it. So
yeah.
I think
you have a slide.
It, but PN junction. Pratam, what I'll do is I'll add as a list of questions that if there's time for next week, I will. If sometimes when we start these live streams at 1 p.m. Eastern that we just mentioned to you, if there aren't any questions too many right away, we have a little bit of window of opportunity right at the beginning to answer some of the questions, like we did this one with the anonymous had some questions.
Mm-hmm.
I can kind of show you band diagrams for a PN junction and what a Mach-Schottky analysis looks like for a PN junction. I'll add that to the list if there's time. I'll try to talk about that a little bit. Okay. But for now, we've sort of reached the end. So
yeah.
But yeah, thank you everybody. We learned a lot. We talked about things being edible. Yeah. We talked about tree bark and some electrochemistry.
There's some electrochemistry in there too.
Yeah.
Just mixed in.
Some children's books.
Yep. Children's books.
And then I ranted about impedance.
Yeah.
This was a good session.
Yes. Good session.
Well, thank you everybody.
And just a quick heads up.
Yes.
We'll be here next week, the 28th of October, or the 21st of October.
Yeah.
Always tune in to the Pine Research YouTube channel. You'll always see an upcoming live stream.
Yeah.
But the following week, the 28th, is a U.S. holiday, or most of us will be off.
Yes.
And I think the following December 5th, we'll be back.
Should be back. Yeah, I'll be back.
But just letting you guys know about changes and
the
stuff.
Last
like that.
weekend of this month is Thanksgiving holiday in the U.S., so we will be gone.
We'll be gone.
So next week we will be here. Then we have a week off.
Yep.
So until then, we will see everybody next week, and I hope you all have a good weekend. Rest of your week, if it's still the Friday for you, and take care.
Bye.